Hi, I'm Gunjan, and today I'm going to be taking a session on trigonometric passion and how it can be useful to solve Olympiad problems. And let's start. So first we're gonna start with defining trigonometric functions. So basically there are a few types of functions: sine theta, cos theta, tan theta, secant theta, cosecant theta, and cot theta. And these may sound a lot, but they're actually related to each other, so it's actually not that complicated. Just a second. So let theta be this angle and it's less than 90. So we define trigonometric functions to describe the size of the angle. Let OA and OB be two random rays and theta be the angle between it. We define sine theta to be PQ by OP, cos theta to be QO by OP, tan theta to be PQ by OQ, secant theta to be OP by OQ, cosecant theta to be PQ by OQ, and cot theta to be, this to be OP by PQ, and this to be OQ by PQ. And that's how they're defined. And the first instinct is to prove that are these functions even well defined? What if these values are not same for this theta and theta in some other side, the same angle in some other arrays? So we can prove that they're well defined. Let's assume they're not well defined. So let's draw P1, Q1. So sine theta is PQ by OP here, and the other sine theta is P1, Q1 by PQ1. And we can see by similarity that these two must be equal, clearly, because the angle is same and these are parallel. So these two are equal, so it's easy to say that the ratios are well defined. And so that's about basics of trigonometry and the ratios. So there's a rule called sine rule. It's also called sine law. It says that in a triangle ABC, with circumradius r, it says that 2r equals a by sine a equals b by sine b equals c by sine c, where small a denotes the side BC, which is a side corresponding to the vertex A, and sine A denotes the angle A. So we can go about proving it this way. let O be the circumcenter. We know that angle BOC is twice angle A, so this is 2A. And if we draw the triangle OBC separately, we can see that if we draw the perpendicular bisector, this angle is A and this angle is A2. OB equals OC, which is both R, and let this be B. So we can see that sine A in triangle OBD is equals to BD by OB. And OB is clearly R and BD is clearly BC by 2. So sine A equals BC by 2R. So 2R equals BC, which is A by sine A. And since this is only dependent on A and 2R is not dependent, like not biased towards A, B or C, so we can say by symmetry that it is also B by sine B, which is also C by sine C. So this is called sine rule. There's also a rule involving cosines. Clearly it's called cosine rule. So it says that in a triangle ABC with the same notations, this is angle A, this is side A, this is B, this is side B, this is C, this is side C. So small a square equals B square plus C square minus 2BC cos A. There are different ways to write this. We can also write this as cos A equals B square plus C square minus A square by 2BC. But I prefer this way more because it's just clearer and you don't need to deal with fractions. So we can go about proving it this way, like we drop a perpendicular from A to BC and let the foot be B. So we know that this angle is B, this angle is C. Let's ignore this for now. Okay, actually let's not draw the B perpendicular. Let's drop the B perpendicular and let this be A. We know that AE is equal to, in this triangle, if you see sine of angle A, that is AE by AB equals sine A. So AE equals AB sine A, which is C sine A, and CE by BC, that is equal to, sorry, not CE, BE by BC. BE by BC equals sine of this angle, which is sine C, implies BE equal to A sine C. Also note that CE, this length is just B minus AE, which is equal to B minus C sine A. So we can say CE equal B minus C sine A and BE equals A sine C. So we know that by Pythagoras theorem, BC square equals BE square plus CE square. Now BE square plus CE square is A square sine square C plus CE square, that's B square plus C square sine square A. Something went wrong. So basically here A sin C, this BE by AC is also in this triangle, BE by AC, that's sin A. So BE can also be written as AC sin A, which is just B sin A. Sorry, AB sin A, which is C sin A. So we can just write this as C sin A, and this becomes C square sin square A. And continuing that, I will just write it again. BE square, which is C sin A square, plus CE square, which is B minus C sin A square. That does not seem right. This is cos A. Oops. So this is cos, this is cos. I'm sorry for messing up again. So yeah, this should be correct. BC square, which is also A square, is C square sin square A plus B square plus C square cos square A minus 2BC cos A. Now we know that cos square A plus sin square A is always 1. So if we add these two, we'll get C square times sin square A plus cos square A plus B square minus 2BC cos A, which is just C square plus B square minus 2BC cos A, and the left hand side is A square. So here is the result, and this is called cosine rule. I hope that's clear. Now the next thing I find very useful is sum to product. Okay, technically product to sum. Sum formula. So let's say you have sine of A times sine of B. So there's a way to write it as sum of two trigonometric functions. So the answer is actually just half cos of A minus B minus cos of A plus B. And it's actually not that hard to prove, because we know that cos of A plus B equals cos A cos B minus sin A sin B. So cos of A minus B will be cos A. Cos B is just cos of negative B is just cos B, and sin A, sin of negative B is negative sin B, so this just becomes plus sin B. So if we subtract this from this, we get half of cos of A minus B minus cos of A plus B equal to sin A sin B. And there are three more formulae that I will use often. They are sin A cos B equals half of sin A plus B plus sin A minus B. And the third is cos of A times cos of B equals half cos of A plus B plus cos of A minus B. And the proof of the other two are on the similar lines only, so I will not go over them, but these are very useful in my opinion at least. So let's just see some applications, because studying all of this just feels useless for now because we haven't seen any problems. So okay, wait, let's go over this too. So people have seen the theorem, Shiva theorem, right? If not, I'll just go over it. The Shiva's theorem says that if AD, BE and CF are Chevins just means a line through a vertex meeting the other point, the other side at a vertex. So if these three are Chevins passing through a common point, let's call that M, then AE by EC times CD by BD times BF by AF is equal to 1. That's what the theorem states. And it's easy to prove using areas, because you can see that AE by EC is just, if you drop a perpendicular, that is just from here also. So AE by EC is area. Okay, symbol of area is this. It's not general, but let's use it. So this is AME by CME, which is also equal to ABE by BCE. That is because area of AME, this area, that is just half ME times AE, and area of this is half ME times CE. So ratio of these two areas is AE by EC, and if we take area of ABE, that's B, oh sorry, not E, this is, let's say X and this is Y. So area of ABE is BY times AE times half, and area of BCE is CE times BY times half. So I'll just write it down. AEM by CME equals half AE times MX upon half CE times MX, and clearly these two cancel out. So AE by CE is the ratio. Similarly, area of ABE upon area of BCE equals half BY times AE by half BY times CE, and again these two cancel, so it's again AE by CE. Let this ratio be, let's say, that is mu. Okay, so let this ratio be K, So we know that for to make writing easy for me, let this area be A, this be B. Okay, let this be A, so this is AK, this be B, so this is BK. So we also know that B minus A times K upon B minus A is also equals to AE by EC. So, and B minus A times K is just BK minus AK, which is just ABE minus AME, which is just area ABE minus area AME upon area BCE minus area CME. If you notice it in the figure, this value is just area ABM and CBM. So this value is just equal to ABM by CBM. So we got that AE by EC equal AMB by BMC. Similarly, we can say that CD by BD equals area AMC by area ABM, and DF by F, not D, BF. BF by FA, that's equal to CMB by AMC. It's easy to see from the figure that this should be true. It's all just symmetry. So clearly, if we multiply these three, you can see that this gets cancelled, AMC gets cancelled, and CBM gets cancelled. So AE by EC times BB, CD by BD times BF by AF is actually just 1. And this theorem is very useful when you're trying to prove if 3 Shivans are concurrent, or just trying to find ratios, or trying to prove if things are parallel. Now there's also a theorem which is on the same lines, which is called trigonometric form of shape. If you see a triangle ABC, Shivans ADBECF, let them meet at M. So that says that sine BAD by sine DAC times sine ACEF by sine FCB times sine EBC by sine EBA equals 1. This is what the theorem says. And it's quite easy to prove using sine rule, and I'll just prove that real quickly. So sine BAD by BD that's sine rule in this triangle. So that is equal to sine of this angle. Let this angle be D, this angle be E, and this angle be F. So that is sine D by AB, which is just C. So we can write sine BAD as BD times sine B by C. And similarly, sine DAC equals, this is just 180 minus D, so sine of that is still D. Sine D by, instead of C, now it will be B, and instead of BD, it will be CD. And so this fraction, this will be sine D BD by C, sine D CD by B. And these two terms get cancelled. So the first fraction is just B BD by C CD. By symmetry, you can just write the second fraction, that is equal to, that is AAE by CCE, and third fraction is equal to, that is, wait, sorry, this is its second. Second is AAF upon BBF. Third is equal to EBs. That is equal to CEC by AAE. Now if you multiply all these three fractions, we get B by C times BD by CD times A by B times AF by BF times C by A times EC by AD. Now if we see the product of these three, first we just cancel the common terms, that's B, C and A. Now we're just left with BD, AD, CD. This is not AD, this is AE. And this is also AE. So we're left with BD, CD, AF, AE, BF, FC. So that's just BD by CD times CE by AE times AF by BF, which is just by Shiva's, the first form of Shiva's theorem, which is just equal to 1. So this is just trigonometric form of Shiva's. And now we'll move on to the problems. I will wait for 5 minutes so people can try. So the problem says that ABC is a triangle, AD, BE and CF are concurrent lines also. But that's not important. And PQR are points on EF, DE, FD and okay, so this is R. This is R, this is Q. EF, FD and DE such that BP, EQ and F are concurrent. We need to prove that AP, BQ and CR are concurrent. So we could like extend these lines and try to find ratios here, but clearly trigonometric form of Shiva's theorem would be a better idea. So technically we just need to prove that sine of BAP by sine of PAE times sine of ACT by sine of PCB times sine of CBP, not B. This is ACR, this is RCB, CBQ, and sine of QBA. We just need to prove this is 1. And sine of BAP is just sine of FAP, and sine of PAE is just BAE. So we can see that sine of this by this, and PCE that's sine of this, and PCA that's this, not P, this is R. Sine of ACR is sine of RCE, and sine of BCR is sine of RCD. Sine of CBQ is sine of DBQ, and sine of ABQ is FBQ. So if you look at triangle AFE by itself, and this is point P, we need this angle by this angle. So sine of, if we apply sine rule in this triangle, let's say, sine of FAP by FP equals sine of, let this angle be P, so sine P by AF, and we know that sine of PAC by PC equals sine 180 minus P, which is same as sine P by AC. So if we divide these two equations, we will get sine of FAP by FP by sine of PAC by PC equals sine P by AF upon sine P by AC. So we can just cancel sine P, and this side becomes AC by AF, and this side becomes sine FAP by sine PAC times PC by FP. So technically we just get sine FAP by sine PAC equals AC by AF times FP by PC one result. And by symmetry, let's just claim the rest results because I don't want to make it very long. So sine of we need sine of ECR upon TCR. Let me just copy paste this. One thing that went wrong was this was E, so this will be E, and this will be E, and this will be E2, this will be E. So sine of ECR upon sine of DCR, that's equal to dr upon ER times ER upon RD and sine of dBQ by sine of ABQ, that is equal to FQ by DQ times I'm sorry, that's equal to FB by BD times DQ by FQ. And you can observe these formulas for a few seconds. And yeah, so now let's just multiply these three. So LHS is the thing we need to prove this one. Let this fraction be not this fraction. This fraction, let this value be S. So S equal to AE by AF times FP by PE times DR by RE times ER by RD. This is supposed to be CE by DC. CE by DC times FB by BD times DQ by FQ. And you know that by Shiva in DEF, this triangle, that FP by PE, this fraction, times ER by RD, that is okay, I think I messed up this fraction. I'm so sorry. ABC times FB, that is ER by yeah, now it seems correct. So generally it's just better to do it all again so you don't mess up like I did, but it's fine. CD by EC times ER by RD. So Shiva in EFT, that gives FP by EP upon times ER by DR, which is this fraction, times DQ by FQ, which is this fraction. Product of these three is 1. And then Shiva's in triangle ABC, we know that BD by DC, BD, okay, let's go other way now. We know AE by EC, which is AE by EC, times BD by DC, which is, sorry, DC by BD, which is DC by BD, times FB by AF, FB by AF, this is also 1. So we just get that value of S equals 1. So that just proves that AP, BQ and CR are correct. Now let's do this problem. So basically whenever you're trig bashing, if it shows up in a contest, it's usually not as obvious, and it usually has some synthetic theory involved with the bash. So when you're bashing and you're not able to bash it completely, so in contests you usually don't get too many questions, so it's better to always write your synthetic claims on a, that's just random, but yeah. I'll wait for 5 minutes so people can try the problem. So the problem says that if ABC is a triangle with orthocenter H, circumcenter O and centroid G, and D be a point on BC such that OD perpendicular BC, that also means that BD equals DC, like it's the midpoint because O is the center which lies on the perpendicular bisector, and HE perpendicular AC, that means E is the foot of altitude, and let F be the midpoint of AB, that's just obvious. Yeah, so we're given that area of ODC, HEA and GFB are equal. ODC, HEA and FGB. erasing. So the first thing that clicks to me is that FGB, that's 1/6 of area of ABC, because this is ABC, this is G. Since this is like these all areas are equal, because G is the centroid and this equals this, this equals this, this equals this, so that areas are also in the same ratio. So area of FGB is 1/6 of ABC. That means area of HEA is also 1/6 of ABC, and ODC is also 1/6 of ABC. So that just means area of ODC, which is half of area of OBC, is equals to 1/6 of area of ABC. That means area of OBC is 1/3 of area of ABC, and area of BGC is also 1/3 of area of ABC. That means area of OBC is same as area of BGC. That means OG parallel BC. That also means that since HG and O should lie on a straight line, because that's the Euler line, HGO parallel to BC. And now we need area of H. We know that AH equals 2 times OD, because this is the Euler line, and that's a lemma that's used to prove the Euler line. And we know that HO is parallel to BC, and G divides the line AD in ratio 2:1. So H also divides it in the ratio of 2:1. So technically HOD is a rectangle, because let this be X. So HX is just half of AH, which is OD. So that's a rectangle. And now area of HEA is just half HE times AE, and area of ODC is half OD times DC, and OD is just, I'll just write it, half OD is half of AH, and DC is just half of BC. Now looking at this triangle, this angle is A, so AE, so basically AE by AB equals cos of A. So AE is just AB cos A, which is C cos A. So half HE times C cos A equals half times half AH by times BC. Now HE by H. Now we have H. If we bring AH from here to here and we look at this triangle, so HE by AH is just sine of this angle, and this angle is 90 minus C, so that is just cos of C. So half cos C cos A times C equals 1/8 BC. So 4 cos A cos C equals A, and A by sine A, we multiply and divide by sine A, which is equals to C by sine C using sine rule times sine A. So technically 4 cos A cos C sine C equals sine A. Now we write it as 2 cos C cos sine C cos A equals sine A, which is 2 sine of, this is just sine of 2C cos A equals sine A. Here, if we chase some angles, we'll also find that so we'll also find that angle AOH, just a second. So angle AOH equals, let this point be K. So angle AKX, because HO parallel XK, and this angle is just angle KAC plus angle KCA. I'll just copy paste the figure. So angle AOH equals angle KAC plus angle KCA, and angle KAC is just 90 minus angle B, and KCA is just angle B, angle C, and so angle AOH is 90 plus C minus B. And sine of angle AOH equals AH by AO. We know that AH is twice of OD, which is OC cos A by AO, and OC equals AO because it's the circumradius. So we know that cos of C minus B equals cos of A, implying angle A equals angle C minus B, or angle angle A equals angle B minus C. We'll be using that while finishing the problem. So we have this, and from the sum product to sum formula, we remember that this side equal to cos plus cos sine of 2c plus a plus sine of 2c minus a equals sine a. If we assume that the first case is true, then angle A equals C minus B, then 2C minus 2C plus A, that is 3C minus B, and 2C minus A is B plus C in the first case. So sine of something went wrong. Just give me a second, I'm so sorry. Yeah, it seems correct. Yeah, so this is just in the first case, that's sine 3c minus b plus sine b plus c, which is 180 minus a, which is sine a, equals sine a. So sine 3c minus b equals 0. That means either this equals 0 or this equals 180 degrees. So if it's 0, then angle B equals 3c, but angle A is c minus b, and angles are positive as we have taken. That's the notation here. So that this is not possible. So 3c minus b equals 180, and c minus b equals a, and we know a plus b plus c is 180. So just c minus b equals b plus c equals 180. So c equals 90 and 270. B also comes to be 90, which is just not possible. So this case does not work. So angle A equals B minus C. So this just becomes, in the second case, this is just B plus C, and this is just 3C minus B. And here 3C minus B equals 0 or 3C minus B equals 180. If 3C minus B equals 0, then B equals 3C, A equals 3C minus C, which is 2C. That means 6C equals 180, C equals 30. Yeah, C equals 30 degrees. Or in the second case of 3C minus B is 180 degrees, then A plus B plus C, which is B minus C, 2B is 180 degrees, then B equals 90 degrees, then 3C equals 270, so 3 equals 90 degrees. And that is not possible because I think something went wrong here. I'm not able to figure out what, but something did go wrong. Okay, let me just see what went wrong. I'm pretty sure till here it was fine. Angle AOH equals angle AKB, which is 90 minus B plus C. Sine of angle AOH equals AH by R, which is 2OD by R, which is cos of this angle, which is cos of A times. Oh, okay, so that's what went wrong. So 2 cos A equals sine of 90 minus B plus C, which is cos of B minus C. Yeah, so 2 cos of A gives cos of B minus C. So we have sine 2C cos of b minus c equals sine A. So 2 sine 2c cos b minus c equals 2 sine A, and this means sine of b plus c plus sine of 3c minus b equals 2 sine A, because 2c plus b minus c is b plus c and 2c minus b minus c is 3c minus a, and this is clearly sine A, so we cancel one of them. So sine 3c minus b equals sine A, so 3c minus b equals a, or 3c minus b plus a equals 180. If 3c minus b equals a, and we know that a plus b plus c equals 180, and we also know that a equals c minus b or b minus c. It can't be c minus b because then angle c equals 0, so it's none. So from here you get 3c minus b plus c equals 180. So angle c equals 45 degrees. That's 180 by 4. And from here you know this. You just equate both of them. So you have 2c equals, a plus b plus c equals 3c minus b plus a. You cancel a. You take b here. And you have 2c equals 2b, implies b equals c. So you know angle 2b plus a equals 180. And we also know that 2 cos a equals cos of b minus c. Here, since b minus c is 0, so this is 1. So cos a equals half, implies angle a equals 60 degrees. Since a is 60 and b equals c, so b and c are also 60, so c equals 60 degrees. So the two angles that work are c equals 45 degrees and c equals 60 degrees, and I'm pretty sure that's the correct answer. So I guess we'll end right now because we covered a lot in this video, and hopefully you had fun and got to learn something new. And I did mess up a couple of times, but I hope that's okay. And we'll meet next time. Thank you.